Okay, let's talk about the area between two curves. And mostly we're going to work on the calculator on this one. We're not going to do a lot of this by hand. So the only difference between an area between two curves and an area under a curve is once again, you need to graph the two curves to look at them before we try to do any kind of area problem, because those two curves are probably going to intersect somewhere. And if they do, we need to find their intersection points. So we're always going to want to graph it first. And example 4 that we're going to wind up with tonight is if an executive knows how the savings from a new manufacturing processes decline over time and how the cost of that process will increase, how could she compute the net savings and when will it cease and what is the total net savings going to be? So that's going to be our last problem. So what we're looking at here is we're talking about the area under the curve of two different functions. And for example, this is f of x and this is g of x. The total area under f of x is blue, and the total area under g of x is pink. But if we wanted the area between f of x and g of x, what we would do is we would subtract the area under f of x because it's larger minus the area that's under g of x, which is smaller. And we would have the area between those two curves. And we have a lot of situations where we've talked about having two curves and looking at the difference maybe of supply and demand. That's actually one of the best examples of needing the area between two curves, because that's probably our last example tonight is talking about supply and demand and equilibrium and what happens before equilibrium, because there's a point where we have something called buyer's surplus and there's another point where we have something called manufacturers or producers surplus. So the area between two curves, the thing that you need to know is that the one that comes first in the subtraction needs to be the curve on top. It has to be the one that's always higher than the other one. If they actually happen to intermingle and have more than two intersection points, then we would have to also do what we've done before and break up and do integration at all of the different intersection points. So this is our first example. We're going to find the area bounded by the curve. F of x is negative x squared plus 1. G of x is 2x plus 4, and we're looking between the values of x equals negative 1 and x equals 2. And this is a picture of what we're looking at. So these are already graphed. And we're trying to find the area that's shaded in blue here. Now when you look at that graph, which curve is always above the other one? F of x or g of x? Now, g of x is always on top, which means when we do the integration to find this area, then g of x needs to be the first function. Okay? So with that sketch in mind, the things that we need to know is which function is greater, and you can set them equal to one another and find out that there's no real roots, but the easier thing to do, honestly, is just to graph the two functions. So, why mess with algebra if you've got a calculator that can show you a picture? So we saw from the picture, we're going to start by subtracting f of x, which is the bottom function, from g of x, which is the top function. And since we have the values of the functions, I'm going to actually go back and pull in the details of how that integration works. So when we set up this integration, we're going to go from x equals -1, which is right here, to x equals 2, which is right here. And we notice that g of x is always on top. And that f of x is always on the bottom. So when we do this subtraction, we want to make sure that that's the order that we subtract the two functions. Okay? And then looking to see, make sure we get the right form for our two functions. We're doing the integral from -1 to 2 of 2x plus 4 minus -x squared plus 1 and then of course we always have hanging out here at the end of it dx. So notice that f of x minus g of x is actually going to be two different functions, and we can actually break that up. But we can also combine the functions. So that's what we're going to do. So it's this whole new function. We're going to simplify it so that we don't have to do 2 or 3 separate integrals by doing the integral from -1 to 2 of 2x plus 4 minus times minus is plus x squared, minus times plus 1 is -1. So this is actually going to be x squared plus 2x, and then 4 minus 1 is plus 3 dx. So even though this is the graph we're looking at, that's actually the function that we're going to integrate. We're going to actually integrate the difference in the two functions. And we're going to do this one term by term. So we're going to break it up into baby steps. And the integral of x squared dx is x to the third divided by 3. And we could add the constants as we go along, but we know they're going to disappear at the end of the problem anyway, so we're just going to let it do that. And this integral is going to be 2x to the second divided by 2, which means ultimately those 2's are going to cancel. And this one's going to be 3x. And since we're evaluating all of them, from -1 to 2, then we can actually do all of those at one time. Yes, it should be plus 3x. Thank you. I forgot to cross my plus sign. Okay? So we're going to first plug in the upper value, which is 2. So that's going to be 2 cubed over 3 plus 2 squared plus 3 times 2. And from that, we are going to subtract -1 cubed over 3 plus -1 squared plus 3 times -1. And of course, we're going to do that on the calculator so that we don't trust my not-so-caffeinated brain anymore to actually do this correctly. That first one is 12 2/3. And the second one is 4 1/3. Two cubed is 8 over 3 plus. Am I right or are you? Okay. So we're going to do that minus the 4 2/3. Now I have to remember how we put these in because I haven't done this in a long time. Oh, 1/3, yes. My bad. And that's 25 over 3. And realistically, that is not as a fraction, please. 8.333. Okay? So this area is 8 1/3 units, whatever those units are. And you're probably thinking, well, if you can do integration on the calculator, can we not just do these on the calculator? And the answer is yes, we can. What you would do first is you would put your top function in y1. And your top function here is 2x plus 4. You might have to graph it first to figure this out. So even if I didn't know that was my top function, I would do x squared plus 1. And then I would also graph 2x plus 4. And I would set my window up so that I could see from at least maybe about -3 to about +3, because I'm going from -1 to 2. And then I'll let the calculator pick a window, and then I'll just refine it to suit what I want it to look like. So there goes one function, and there goes the other. And we're really not that interested in seeing all this up here and all this down here. We just really need to see the parts that are in between there. But that'll do. This looks enough like that that it's okay. So the calculator chose to go from -8. Well, we don't really need to go to -8. We could go to -4. And 10's fine, but we could stop at 8 because we don't really need to go that high. And that looks a little bit more like the graph that I've got over here on the side. But it still shows us the same thing. So then how are we going to do the integral? Well, the first thing you want to do is you want to hit your trace button. If you don't, I hope at this point it's obvious to you that the linear function is the one that's on top, which is y2. But if it was another class, I would want to make sure that they understood that. So if you need to, hit trace and make sure which function's which. So y2 is the top function. So you go back to your y equals, and you want to put in y2 being the first function. And the easiest way to do that without having to retype a bunch of stuff is hit your vars key and go to y vars and choose y2 minus vars over to y vars function y1, because you want the top function minus the bottom function. And at this point, what you want to do is you want to turn those first two functions off. Because if there's three functions on and you hit function integral, your calculator's eyes are going to cross because it isn't going to know which one to do. So you want to only have what you want to actually integrate set up to where it's going to graph. So by putting your cursor over the equal sign, you've turned off the functions, but they're still there. They're just not going to graph. Okay? So it's not actually going to show us the graph that looks like this. It's actually going to show us the graph of the integral that we did. So then we're going to go second, trace, choose number 7. And the lower limit here was -1. And the upper limit is 2. And so the total area that's equivalent is 15. And that makes me think I did something wrong. I think I probably did. Because it worked earlier. What did I do wrong? Let's try the numerical integration instead. I'm not so sure that's right either. Oh, I know it's not right because that said function max. Never mind. Oh, it says it's 15. So why am I getting 8 1/3? Let me see if I can follow what we've got here. So this is 2 to the third is 8 over 3 plus 4 plus 6 minus -1 cubed is -1 over 3 plus 1 minus 3. That would be positive. That would be negative. Okay, but they just combined it into 2. So yeah, that'd be positive 2. 2 to the third is 8 over 3 plus 4 plus 6 minus -1 cubed is -1 over 3 plus 1 minus 3. That would be positive. That would be negative. Okay, but they just combined it into 2. So yeah, that'd be positive 2. 2 to the third is 8 over 3 plus 4 plus 6 minus -1 cubed is -1 over 3 plus 1 minus 3. That would be positive 2. So yeah, that'd be positive 2. 9/3 would be 3 plus 10 plus 2. Now, the answer is 15. The answer is 15. I'm not sure how I managed to get 25/3, but the answer is 15. Which is why it's good to trust your calculator sometimes. But the thing here is, and I had forgotten this, you can't actually get it to graph. You can't get it to graph this integral when you're going the difference between two functions. It won't do that. It won't show you the graph, but it will give you the right area numerically. So the place that I got that function was the same place we got n-deriv. It works just like n-deriv does. And I didn't have to have actually used the calculator y1 and y2, because we could have just gone math, function integral, and the top function is 2x plus 4. Minus the bottom function is negative x squared plus 1. And then the second argument is going to be always, what's the derivative with respect to? Well, that's always x. And then the last two pieces of information are your lower and upper limits. So from -1 to 2. And it is 15. And I still don't know what I did wrong when I got the answers I got. Oh, yes, I do. Yes, I do. I just saw it. What I did wrong is this actually does come out to be negative. This area comes out to be negative. So I should be subtracting a negative, which makes that positive. So 12 2/3 plus 4 1/3, well, no, that would be 16. That would be 17. That's not right either. I don't know what I did. Never trust a math teacher to do arithmetic at night. So it's a good thing we have the integral and we can do it numerically. So before I move on, does anybody have any questions about how to do that one? Just be very careful evaluating your arithmetic, and then also be sure and back yourself up using your numerical integration on your calculator. So as long as you show me your work, I'm happy with it either way. So here's two more curves. We're going to do it with calculator first. And like I did before, I'm going to leave that there, but I'm going to put x to the 1/2 power in first, and then x cubed in second. And for this one, you really would just have to play around to find a proper domain. You might even want to start on your standard window. Just to get an idea. So there goes one of the functions. There goes the other one, and we can see that the place that they're overlapping is in close to the origin. So that says we probably need to narrow that in. So there goes one function. There goes the other one, and I see here that my window's way too tall. So I get a pretty good picture right there. So I need to know where these things intersect. And it's fairly easy to see that they're going to intersect at 0, because 0 to the 1/2 is 0, and 0 to the 3rd is 0. So they're going to intersect at 0. That one you can kind of observe. But the other part is not as easy, so what we want to do is we want to find out the x value where they intersect here. So we go to second trace, choose number 5, and hit enter 3 times. So our second intersection point is at x equals 1. That means we're going to integrate this from 0 to 1. So that's how you find your limits, because that's how you find the area's containment points. And then looking at the graph, we notice that the one that's always on top is x to the 1/2. So that's the integral that we're going to do. So we're going to use the calculator to actually do the integration. We're going to go to the function integral. And since we've got them in here at y1 and y2, we can do that. Actually, what I'm going to do is I'm going to come down here and say that y3, because I think this will work, y3 is going to be y1, which is the top function, minus y2, which is the bottom function. And I'm not going to try to do it from the graph, but I am going to go back over here instead of trying to type all that in. I'm going to tell it to do the integral of y1 minus y2, which is in y3. Bless you. With respect to x, going from 0 to 1. And just in case it comes out to be a fraction, I'll ask it to give me the answer as a fraction. It may or may not work. Wouldn't be first time. And actually that would be a fraction, but it doesn't matter that it is a fraction, because that's a close enough approximation that when I look back to see what they got, they got 5/12. Which is what I got. Okay? Only we didn't do any arithmetic, because at this time of night we're tired of fractions. Okay? So unless I tell you for some reason that I wanted to see this, which I am not likely to do, I might tell you to sketch me the graph to verify which one is supposed to be first and which one's second, and then expect you to do it on the calculator. That way we eliminate any chance of making arithmetic mistakes. Okay? Because I know y'all work all day before you get here. And this is explained in the PowerPoint, and I will have the PowerPoint posted along with the recording in that folder so you can look at it to refresh your memory. And on the 83, it actually looks like this. You fill in the blanks so that it looks like what you put on paper. Now, this is one where you could get in trouble if you weren't careful. Because part of this one goes below the x-axis and part of it goes above the x-axis, and your calculator, being the brilliant little thing that it is, would not do that properly. So on this particular one, we have to be very careful. So what you're going to have to do first is, for one thing, y equals x is the top function as long as you're going from 0 to 3. But x squared minus 2x is the top function when you go on past 2 to 4. So you need to break this one up, which is why they went from 0 to 3 with x minus x squared minus 2x, and then went from 3 on to 4, putting the other function first. So we have to do two separate integrals. Now there's the calculus part of it. So for the first part of the integral, x comes first. And x squared minus 2x comes at the bottom, so we put it on the bottom. And that's with respect to x from 0 to 3. Yeah, 3. And it says that's 4.5. Now, if we want to be sure that's right, that should be this part of the integral. And that's 4.5. Okay? So this part of it matches. So then we're going to do the next part, and we're going to change places. And y equals x comes second, and the quadratic comes first. And then our limits change from being 3 to 4. And that comes out to be 1.8333, which is a fraction. It is an improper fraction, but we're going to be satisfied to add 4.5 to that. Which gives us 6.333, which is exactly what 19 divided by 3 actually is. So you can do that whole problem on your calculator, but again, you would want to graph it and find those intersection points first, and then break it up into two subregions. Okay? So this is example 4, and this is probably where we're going to stop. Company is considering a new manufacturing process in one of its plants. The process provides substantial initial savings, but the savings decline over time according to the rate of savings function S prime of t equals 100 minus t squared. And S prime of t is in thousands of dollars per year. So at the same time, the cost of operating the new process is going to increase with time because other things go up. According to the rate of cost function in thousands of dollars per year, C prime of t, which is t squared plus 14 over 3 times t. How many years will they realize savings, and what would be the total net savings during that period? Well, this is the graph. If you graph C prime of t and S prime of t, what you see is that C prime of t is on top because cost is more than the savings to begin with. Okay? But then after a period of time, your cost increases beyond the savings. So we want to know, where did those two intersect, because that was when cost and savings equaled each other out and savings was over with. So you can either set them equal to 0 or you can graph them both. Well, let's see, that's going to be x squared. And the other one is x, oh wait, that's it, forgot the 100. (100) minus x squared for one function, and the other one is x squared plus 14 over 3 times x. And we'll take a clue from the graph they already gave us so that we won't waste time looking for a window. So we're going to go from 0 to 10. And from negative 25 to 125. So when you look at your graph, we want to find the intersection of those. The intersection point is at x equals 6. So what we want to do is we want to integrate the difference in those two functions from 0 to 6. And the top function, of course, your first is s prime, which is the 100 minus t squared. So it's going to be 100 minus t squared, which is in the y1 position, minus the y2. So we'll do the numerical integration. Not there, though. We'll do the numerical integration of y1 minus y2 with respect to x from 0 to 6, and the total savings is $372,000. And that's over that 6-year period. Okay? And I'm trying to show you how to do these the way that I would do them if I were doing them on a test, rather than trying necessarily to do all the antiderivatives. You'll have those to do in class on an exam, but you won't have to do all of this kind of stuff for the exam. Now, you could have just typed in those two equations if you wanted to, but since you'd already graphed them, it saves you a few keystrokes. Okay? And then our last example, and actually on this one I posted the PowerPoint, I showed you the whole integration thing. And this one actually will give you the right answer if you do the integration on the graph. I don't know why the other one didn't. This one's going to take a little bit of thought before we actually look into how to do the problem. Doing the problem is not any harder than any of the others we've done. Consumer surplus occurs when the consumers are willing to pay a higher price than what they can actually pay. You know, you decide that you're going to paint your back porch, so you go to Lowe's and you're going to, you know, you figure it's going to cost you $10 a gallon for paint. And you get there and paint's on sale, and it's only $7 a gallon. That means you saved $3. Well, you didn't save it, you just didn't spend it. That was $3 more you would have paid that you were willing to pay, but you didn't have to pay. So that $3 stays in your pocket. That's called consumer surplus. Okay? According to supply and demand, an item will sell at the equilibrium price where those two curves intersect, but some customers might still be willing to pay more than what that equilibrium price is. So the way that we calculate consumer surplus is we're going to take the demand equation. Remember, D of Q actually sets the price. And we're going to subtract the initial price or the equilibrium price from that. Now, on the other hand, we also have something called producer's surplus. And that's when the manufacturers are willing to supply the product at a price lower than the equilibrium price. So they actually are willing to charge less, but they charge the equilibrium price, so they have more money to put in their pocket. Well, the producer's surplus, you take the equilibrium point minus the supply quotient, which again is a function of price. That's actually a way of expressing the price. This is equilibrium price minus the supply price function. So in this case, here's your demand equation, your demand curve, and anything before equilibrium is the consumer surplus. This is your supply curve, which is also a form of the price, and until you get to equilibrium, that pink area represents the producer's surplus. If you graph those two curves together, which is ultimately what we're going to do, I'm going to skip ahead a little bit. When you graph those two curves together, the supply curve and the demand curve, what you have is your consumer surplus is all of the area above the equilibrium price. And your producer's surplus is all of the curve that's below the equilibrium price. Okay? And that equilibrium price is $85.25 in this case for selling 8.9145 units. Now, realistically, we know you can't sell 8.9145 units. You either sell 8 or you sell 9. So what you do then is you would calculate both of these at 8 and at 9 and see which one gives you the best value, which one gives you the right answer. So we're going to go back and just kind of quickly go through the steps. I'm not going to keep you here over tonight. So here's the price setup. The price in dollars per ton for Oak Brand is D of Q, and that is a price. It's a price depending on the demand for Q units. is 344 minus 3 times e to the q over 2 power. And the demand for the product is q tons. Suppose that the function S of q describes the price where the supply is q tons. And that's going to be e to the q minus 1. Find the consumer surplus and the producer surplus. Here's how you do that. You graph both of those functions together, and you find out where they intersect. That's your first step. So I've entered the demand in Y1, the supply in Y2. I started out on a window from 0 to 10, and if I hadn't seen it there, seen where they came together there, I would have expanded it until I could find the equation. But I always change the domain. I never change the range. I let the calculator do the range for me until I find a window where I can see where those two intersect. I just keep widening the domain. And this is the window that I wound up at. So when I found this intersection point here, using the calculator, the intersection point is 8.9145, and that means that this is 8.9145 tons of oat bran, because that's quantity, at $85.25 per ton. Now, this is the algebraic solution, which I did not do. That's why I showed you the calculator first. So what we're going to do is the integral from 0, where you make none, to 8.9145. And for the demand of 8.9145, then what we're going to do is the integral of 344 minus 3e to the q over 2 minus the 85.25. That's the equilibrium price. That's where that comes from, and this is your demand equation. And when you simplify this by subtracting the 825 or 85.25, it comes out to be that, which is an easier choice. And then you do your integrals. I did these on the calculator. And the reason that you subtract that is because that's where the equilibrium point is. So you want that to be the bottom of your area. And that comes out to be 1795.13. Okay? And it comes out the same way on the calculator. That means the consumer surplus is $1,795.13. Then you want to go to the buyer's surplus, which means you're going to take the 85.25. I'm sorry, the producer's surplus, not the buyer's surplus. You want to take 85.25 minus their supplier's price, and you want to do the same integration with it. And when you do that, it comes out to be $598.38, both on the calculator and doing the algebra. So the producer's surplus of $598 is a lot smaller than the consumer's surplus, and that's another actual example of elasticity. It's because the demand curve is more elastic than the supply curve is. So the demand stayed pretty elastic, but the supply curve was pretty steady, but it didn't have much room to give because they had greater constraints.